Now let's look at the issue of how we predict a target's radar cross-section. First, let's look at measurement. The techniques that we can use to determine our best estimate of the radar cross-section is we can make full-scale measurements. We can see here's a missile, and it's on a large pylon. And then we can make scale model measurements where we make a smaller than life-size scale its features and measure it at a different wavelength or frequency, scaled appropriately, everything, so that it isn't as physically and cumbersome as taking a 40-foot missile or something like that. And then lastly, we can mathematically predict. And this is the one we're going to spend a lot of time on. But let's first look at the measurement techniques. Now, full-scale measurements are done really straightforwardly. You have a range. I think we'll be showing you a photograph in a moment. Here's what we have is a target on a support. And the targets are usually on a column of foam with the dielectric properties of the foam close to that of free space. And of course, you put inside here metal, or have a metal pylon mounting shaped to reduce radar reflections. And then we can subtract the background. You can collect the scattered electromagnetic field with and without the aircraft on it. And you have to do this on a large range where you have to deal with other issues. At a scattering range at Holloman Air Force Base, here is a full-scale measurement of what is known as a Johnson Generic Aircraft Model, a JJAM. And it's a very smooth object that is used for testing radar cross-sections. And it's got a perfectly smooth cone for the nose, a perfect cylinder, and you see these just perfect sheets of wings and tail caps. And so you can look and see cross-section variation and how well how well you can predict what the cross-section is of this relatively simple model of an aircraft. And this is the RATSCAT measurement at X-band, an elevation degree of 7 degrees with vertical polarization. And here is the cross-section of the end cap, the fuselage specular, the cones specular, right here, the wing leading edge and trailing edge. And so you can see, and so the obvious symmetry on the other side of 0. This going from minus 180 degrees to 0 degrees, and then up to 180 degrees. Tail, this is the nose, and that's the tail. And here's the cross-section in dBSM. You can see it goes down from minus 25 dBSM to 15. So there's a 40 dB range of cross-section just on this target. So this shows you that we can make good measurements. Another way we can make measurements is with a compact range. And this is one at Point Mugu. They have a radar reflectivity, the Air Force Research Lab in Point Mugu. Here's that compact range. We see a low RCS pylon, a target on the top of the pylon, and this is the mechanism that they'll generate in a small region a plane wave. They'll have a feed antenna sending out the beam to a subreflector and then coming up to the main reflector, which is shaped so that a plane wave will come out of it and impinge on the target. And then the data will come back and be received and so that one will be able to calculate the scattered electromagnetic scattered field as the target is rotated. Now here's how you do scale model measurements. And here we see an MQM-107 drone, and it's at 0.29, roughly a third, a 30th, and a 100th scale sizes, where this is a 1 foot. So this would be a 1 foot scale. So what one would do is you take your full scale target, measure at frequency f, and then if you take the scale factor s, reduce it in size, dividing by that s factor, and then you measure at a frequency s times the frequency that you want the data at, you'll have the scaling. So in other words, make a scale model that's a tenth the size of the real entity at 10 times the frequency, and then you'll have effectively, if we're just talking about a perfectly metallic substance, perfect conductor, in a minute, we'll show you the other scaling factors, then you'll have the full scale cross section. And these are how the different quantities scale. These are the laws for scaling of the RCS of targets when we're making measurements with subscale models. If this is the full-size model and it's down to a factor of 10 smaller in size, then the scale factor is 10. So the primed numbers are the values you'd have to have for the scale model divided or multiplied or divided by this factor of 10 if it's a 10th scale model. So for a scale model that's a tenth the size, you take the length, divide it by 10. And the wavelength will be divided by 10. You have to multiply the frequency of the radiation by 10. And the time, divide by 10. Permittivity and permeability remain the same, and the conductivity has a scale factor of 10. This is sometimes very hard to do when there are strange conductivity substances in your main model is getting the subscale model's conductivity at this right G prime. And then the radar cross-section of the primed measurement in the subscale domain will be the real cross-section divided by that scale factor. I used 10, but here it's S squared. Okay, now let's go over theoretical calculations, and this is going to be a large part of the talk. First, let's introduce and look at a few simple problems, the ones that are tractable and easy, and then we're going to look at some exact techniques and some approximate techniques and compare the different methodologies. Here we have the radar cross-section of a sphere normalized to pi a squared, the area subtended by the sphere, as a function of the circumference divided by the wavelength. And both of these scales are logarithmic. And they divide down into regions. The Rayleigh region, where the wavelength is much, much larger than the size of the sphere. And this goes as 1 over lambda to the 4th. And then the optical region, where the size of the sphere is much, much greater than the wavelength. What I'd see of a sphere if I looked with my eye with 1,000 angstroms, I looked at a sphere a foot in diameter. And then we see these fluctuations. So what would appear to be an interference effect. And here we go over just what I said, 1 over lambda, constant over lambda to the fourth. And in the optical region, and surface and edge scattering occur. And then there's this region right here, which implies a resonance. It's called the me region. It's called the resonance region. And it's hard to calculate this for most objects. I remember in an electromagnetics class, my senior year at MIT, the professor drew a relatively simple object, and he plotted the cross-section, and then of what it looked like. I think it might have been, it's so long ago, a sphere. And in this region, he just drew, he said, it's easy to calculate this. We can do it with approximations. It's easy to calculate this. It's the optical region. And then he had this other region in between. It could have been a sphere, it could have been arbitrary. And then he just drew a skull and crossbones and said, this is not easy. So when you have scatterers on the object that are the same size as the wavelength, you have oscillations, backscattered waves, interferes with the creeping wave for the sphere, and for other more complex objects. This is the simplest object you can imagine. Its cross-section does not change with aspect angle. It's the simplest. And you still have interesting effects taking place here that are non-trivial. So we have 3 regions to worry about. There are a bunch of other relatively simple shapes, and some of these cylinders, flat plates, rods, cones, and ogives, some are amenable to relatively straightforward calculations in some wavelength regions. And that alludes to the skull and crossbones area talked about. Complex targets such as aircraft, missiles, and ships, the RCS changed significantly with small changes in frequency or viewing angle. And I showed you, I give references and I've showed you pictures of that. And we're basically going to spend the rest of the lecture studying the different basic methods of calculating radar cross-section. Now, in high frequencies, we can make some approximations and get good approximate RCSs, cross-sections, of these kinds of objects. Okay? And a corner reflector, and we'll see that's just 2 perpendicular plates where the beam comes in, bends down, goes back. On the axis of symmetry along the line of sight, it's 4 pi times the effective area that the beam sees divided by the wavelength, a flat plate perpendicular to the line of sight, and a singly curved surface perpendicular to the line of sight. They go as 4 pi a squared divided by lambda squared. A doubly curved surface, that goes as the perpendicular to the line of sight as pi times a1, a2, where these are the 2 radius or mean radius of curvature along the lines. Then we have a straight edge. The edge perpendicular to the line of sight is lambda squared divided by pi. A curved edge, well, the edge element perpendicular to the line of sight is a, which is the radius of the edge contour multiplied by lambda over 2. And then a cone tip goes as lambda squared times the 4th power of the half angle of the cone. And that's at axial incidence. So for a cone, nose on, the cross-section goes as lambda squared and that cone angle. But notice these are always perpendicular to the line of sights. They're not off edge off line of sight axes. These are just approximates under certain conditions. And as I said, now let's look at some complex targets and what the issues are. Well, the problem is, and as I went over that a little bit before and we'll reiterate it again, a plane wave with electromagnetic field E sub I, and I'm just going to deal with the electric field vector of the plane wave. You can get the magnetic field from the plane wave by simple calculation. That's simple to someone who really knows electromagnetism at the level which I'm expecting you guys and women to know. Impinges on the target of interest, and some of the energy we've talked about scatters back to the radar antenna. And here's the definition of the cross-section. So all we need to do is use Maxwell's equations, all the joke, to calculate the scattered electric field. And as I say here, it's easier said than done. Before we look in detail at these different techniques, let's look briefly at the necessary electromagnetism concepts and formula in a few view graphs that should be reasonably familiar with and that we've gone over earlier. Here are the source-free regions in space, and here are Maxwell's equations in a source-free region of space, and the free space constitutive equations, which relate the flux with the fields, both electric and magnetic, and here are the free space permeability. And these are the time harmonic forms. There. Now let's look at boundary conditions. And this is the key thing. The tangential components of E and H are continuous. And this follows directly from it. When you have medium 1 and medium 2 with mu1, mu2, epsilon 1, epsilon 2, and we've got an electric field on one side, magnetic field, and this is the normal. For surfaces that are perfect conductors, the electric field in the conductor, at the conductor, has to be 0. So we're going to have an induced, and since these are time-varying electric fields, we're going to have time-varying magnetic fields and vice versa. And so we'll get currents induced. And the radiation condition, as R goes to infinity, the electric field goes as 1 over R. We've talked earlier in the electromagnetism lecture about scattering about the different polarizations. And there'll be different reasons for using different polarizations. Vertical, which would be vertical relative to the horizon, and horizontal relative to the horizon. For an arbitrary electric field, scattered field, some of it will be, this is a vector made up of the electric field in the vertical scattered, the scattered electric field in that's vertically polarized and the scattered electric field that's horizontally polarized, times this product, times a scattering matrix. And this scattering matrix relates how the scattered field is related via the polarizations. And for reciprocal medium and for monostatic radars, the cross-section, if you transmit vertically and receive horizontally, is equal to the transmitting horizontally and receiving vertically. And the cross-section is equal to 4 pi times the amplitudes, I might note, of these magnitudes of these scattering elements of the scattering matrix. And for circular polarization, the sigma RR, and these would be the basis you'd use instead of vertical and horizontal. Now let's look at predictions in detail. The first one we're going to look at is the finite difference time domain method. And it's an exact method, and we solve the differential form of Maxwell's equations for the exact fields. And as with every one of these methods, there's going to be the pros and the cons.